the product rule. Suppose that we want to find the derivative of two functions that have been multiplied together. One of the things that we need to do is consider the definition of derivative. Turns out we cannot just take the derivative of the first function times the derivative of the second function. The formula is a little more complicated than that. So let's start with the definition. So remember, when we use the limit, we're going to be taking the limit of f of x plus h minus f of x all over h. So if the function that we're considering is f of x times g of x, this gives us the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x times g of x, all divided by h. Now in math, we have something called the creative zero. So we can add something to a function as long as we also subtract it. So in red here, you can see that I've created this nice little creative zero where I'm subtracting minus f of x times g of x plus h plus f of x g of x plus h. These would normally cancel each other out, but I'm putting these in order to get what I need to finish this problem. Now, I'm going to group some things together. I want you to notice the first two terms in the numerator. So here, both of these terms have a g of x plus h. So I'm going to take that g of x plus h and I'm going to factor it out. So if I factor out the g of x plus h from both terms, I'm left with f of x plus h minus f of x over h all times this g of x plus h. So there's the g that I factored out. Now, I can split this up into two different functions here because they both have the same denominator. So I'm going to do something similar with the last two terms. I want you to notice that within the last two terms, they both have an f of x. So I'm going to factor that f of x out to the front, and that leaves me with g of x plus h minus g of x over h. Now, at this point, I want you to think carefully about our definition of derivative. Remember, if we have the limit of two things that are separated by addition, we can take the limit of each piece individually. If you look at the first term we see in our limit, f of x plus h minus f of x over h, that's exactly our definition of derivative for f prime of x. So this term right here is going to turn into f prime of x. Now our second term, if h goes to 0, leaves us with just g of x. Our third term is just f of x, so that can stay the same. And then this last term here is exactly the definition of derivative if our function was g, so g prime of x. So that means when I actually take this limit, I get f prime of x times g of x plus f of x times g prime of x. And it turns out that that is how we calculate the derivative of two functions multiplied together. So that forms what we call the product rule. One of the things I want you to notice about the product rule is that we're using multiplication and addition. Both of these things can be swapped around as we move along, so order is not so important. And what that means is we have two functions multiplied together. We're calling one of them f of x and one of them g of x. And it doesn't actually matter which one you pick to be f of x and which one you pick to be g of x. But the convention is that we pick the first one to be f of x and the second one to be g of x. So let's take a look at how this works. Example 1. Find the derivative of y equals x squared times e to the x. So here we see that we have two functions multiplied together. So since they are multiplied together, I know that I have to use the product rule. So I'm going to do my work on the side because in order to use the product rule, I need to separate out my functions and find each of their derivatives. So the first function I'm going to call f of x, which is x squared, and the second function I'm going to call g of x, which is e to the x. Now I want to find each of their respective derivatives. These derivatives should hopefully be a lot easier than the ones that we started with. So the derivative of x squared is 2x. The derivative of e to the x is e to the x. So now my formula says I'm going to do f prime of x times g of x. So I get 2x times e to the x plus f of x times g prime of x, or x squared times e to the x. So that gives me the derivative of my function. One of the things I want to point out here is that we're calling each of these individual functions f of x and g of x. Sometimes we call the whole function f of x. So in order to avoid confusion, sometimes when we do our side work, instead of using f of x and g of x, we just use f and g, but it still means the same thing. Let's look at another example. Example 2. Find the derivative of y equals ln x times e to the 6x. So again, I see that I have two functions multiplied together, and that tells me that I should be using the product rule. So I'm going to go ahead and I'm going to call the first function f of x, which is my natural log of x, and my second function g of x, which is e to the 6x. Now when I find f prime of x, I can just take the derivative of the natural log, which is 1 over x. But in order to find g prime of x, I need to use a chain rule. So I'm going to go down below and I'm going to say, okay, for an e to something complicated, z is going to be the power of e, which is 6x. And dz dx, the derivative, is 6. And my chain rule said that I'm going to have e to the z, which is the same thing back, times dz dx, so times 6. So I have to use the chain rule to get my g prime of x. But now that I have that, I can plug it into my formula. So I'm going to do f prime times g. So I have 1 over x times e to the 6x from my f prime times g plus f of x times g prime of x. So the natural log of x times e to the 6x times 6. So notice that I have two terms added together. When you do a product rule, you're generally going to have something of this structure where you have two things multiplied together plus another two things multiplied together. Sometimes there's three things if you had to use a chain rule. Example 3. Find the equation of the tangent line to f of x equals cosine x e to the x at x equals 0. So we know that in order to find the equation of the tangent line, we need to know the point where the tangent line touches, and we need to know what the derivative is at the point we're interested in, because that will give us the slope. So f of 0 means I'm going to take 0 and I'm going to plug it into my function. So cosine of 0 times e to the 0. Cosine of 0 is 1, and e to the 0 is also 1. So 1 times 1 is 1, which means my point is going to be 0, 1. The point where the tangent line touches this function is at the point 0, 1. In order to get my derivative at 0, I'm going to have to use a product rule to find the first derivative of this function. Now here's a case, like I mentioned before, where we're calling this function f of x. So when we do our side work, it might be confusing to call our functions f of x and g of x. So instead I'm just going to call them f and g to remember that I'm just doing this on the side. So my f is cosine x and my g is e to the x. The derivative of cosine is negative sine, and the derivative of e to the x is e to the x. So now I'm going to do f prime times g. So over here I have negative sine x times e to the x plus f times g prime. So cosine x times e to the x. So if I want to know the derivative at 0, negative sine of 0 times e to the 0 plus cosine of 0 times e to the 0. Now sine of 0 is 0, so 0 times 1 is 0. And then cosine of 0 is 1, and e to the 0 is 1. So I have 0 plus 1 equals 1. So the slope of my line is 1. So that gives me y equals x plus b. Now I can plug in my point to solve for b. And my point again was 0, 1. So y is going to equal 1 when x equals 0. So that tells me that b has to equal 1. So finally, the equation of my line is y equals x plus 1. So I was able to find the equation of the tangent line that touches the function cosine x e to the x at x equals 0. Again, the process is the same as we've done before for tangent lines, only now the derivative is a little more complex. For the next problem, we're going to be looking at both first and second derivatives. Let's give it a try. Example 4. Find the first and second derivative of f of x equals ln x times x to the fifth. So like before, if we want to find the second derivative of a function, we need to apply the rules that we know about derivatives to the first derivative of the function. So in this case, we'll start with the first derivative and then use that to find the second derivative. So our first derivative here, we're going to find by using the product rule. We have two things multiplied together. So I'm going to call the first function f and the second function g. From there, I'm going to find each of their respective derivatives. So the derivative of the natural log of x is 1 over x, and the derivative of x to the fifth is 5x to the fourth. Now, applying my product rule, I'm going to have f prime times g. So I have 1 over x times x to the fifth plus f times g prime. So the natural log of x times 5x to the fourth. I want you to notice that I can simplify my first term a little bit. So if I have 1 over x times x to the fifth, the x on the bottom will cancel one of the x's on the top, and I can simplify that to x to the fourth. So I'm going to do that before I go to my second derivative. The second term, I'm going to leave it as is. There's not too much to simplify there. So now I have my first derivative. And now from here, I want to find the second derivative. Now the first term is x to the fourth. So to get the second derivative, I can just take the derivative of that first term, no problem. Power comes down, subtract 1 from the power. However, the second term, I notice, is two things multiplied together. So I have to do another product rule in order to get the result of the derivative of the second part. So again, I'm going to pick my first function to be f and my second function to be g. Then I'm going to find each of their respective derivatives. So the derivative of ln x is 1 over x, and the derivative of 5x to the fourth is 20x cubed. So now I'm going to do f prime times g. So 1 over x times 5x to the fourth plus f times g prime. So plus the natural log of x times g prime, which is 20x cubed. And again, I'm going to simplify that middle term. So here, 4x cubed stays the same. Now, the x here from the 1 over x will cancel one of the x's from this x to the fourth. So that's going to leave me with 5x cubed. So my last term here, I don't need to simplify anything. So I have the natural log of x times 20x cubed. And that is my second derivative. So again, I was able to find my first derivative using the product rule, and then I was able to get to my second derivative using the product rule again for that second term. Let's try another example. Example 5. The wave function for a harmonic oscillator, i.e. a vibrating chemical bond, can be written as psi equals a e to the negative x squared, where x is the distance from the equilibrium position and a is a constant. Part of the process of working out kinetic energy of the moving atom deals with derivatives of this particular function. So here, part A, we want to identify the independent and dependent variables for this equation. So here, I was told that A is a constant, and I also know that E is a number. Since x is the distance from the equilibrium position, x must be my independent variable. So my independent variable is x, and my dependent variable is this funny looking thing on the left, which is psi. It's a Greek letter used when we talk about the wave equation. We now want to find the first derivative of this function. So when I take the derivative, I have to remember what my independent variable is. My independent variable here is x. So I'm looking at what's happening in terms of x. So when I think about the first derivative of this function, one of the things I notice is that I have e to the negative x squared. So that's going to be a chain rule because I have this negative x squared in the power. So I have to do a little side work here. My z is going to be negative x squared, and my dz dx is going to be negative 2x. So now, when I come back here and I look at my equation and I think about the derivative, psi prime, I have to use the constant multiple rule, which means I'm going to start with the a. The a is a constant that's going to multiply my derivative. And if I have e to the z, then that means that the derivative is e to the z, so again, e to the negative x squared, times dz dx, so times negative 2x. So my first derivative for the function looks like this. Part C, find the second derivative of this function. So the second derivative of this function is even more interesting than the first derivative, because not only am I going to have a chain rule, I'm also going to have a product rule. So here, if you look at the first derivative, you can see I have two functions multiplied together that both contain the variable x, which means I'm going to have to separate them out into f of x and g of x so that I can use the product rule. So here, my first function I'm going to call f, so a e to the negative x squared, and my second function will be my g, which is negative 2x. Now I'm going to find each of their respective derivatives. Let's start with g prime. The derivative of negative 2x is negative 2. The derivative of a e to the negative x squared, well, that's exactly what we found when we were finding the first derivative. So we already know the answer to that. It's a e to the negative x squared times negative 2x. So now we need to do f prime times g. So remember, we're calculating the second derivative. So we have a e to the negative x squared times negative 2x times negative 2x plus f times g. So here, that's going to be plus a e to the negative x squared times negative 2. Now we can simplify out this a little bit with some of our algebra. So let's see what it looks like if we simplify. So from the first term, notice I have a negative 2x times a negative 2x. So I can combine those, and that will simplify into 4x squared. So ae to the negative x squared times 4x squared. Now here I'm going to pull the minus to the front and write this as minus 2a e to the negative x squared. I could have left the 2 at the end. That would have been perfectly fine as well. But I decided to pull it up front because a lot of times we like to group our constants in the front. But this is a good way to represent the second derivative now with all of our terms, remembering that a here is a constant. Let's take a look at another problem. Example 6. Find the derivative of f of x equals sine of x cubed times the natural log of x squared minus x plus 1. So here, we need to figure out what we're doing first in terms of the types of techniques we know about taking derivatives. I see a lot of things in this problem that are going to include the chain rule, but what I notice most of all is that I have two functions multiplied together that can be completely separated by that multiplication mark. So I'm not going to start with the chain rule. Instead, I'm going to start with the product rule, and I'm going to have to do some chain rule along the way. So here, I'm going to call the first function f. So that's going to be sine of x cubed. And then my second function is g, which is the natural log of x squared minus x plus 1. Now, in order to find the derivative of sine of x cubed, I notice that I have a composite function that's been raised to a power. So for my substitution, my z for this part is going to be sine x. So I also need dz dx. Derivative of sine is cosine. So remember, with parentheses to a power, the derivative is 3z squared, but my z is sine x. So the power come down, subtract 1 from the power, times dz dx. So times cosine of x. In order to get g prime of x, I also have to do a chain rule. For the g prime of x part, my z substitution is going to be x squared minus x plus 1. And my dz dx is then 2x minus 1. With the natural log, our shortcut said we're going to have 1 over z times dz dx. And usually what happens is that the dz dx gets multiplied into the numerator. So that means I'm going to have 2x minus 1, my dz dx, times 1 over z. But my z is x squared minus x plus 1. So I had to use a chain rule for both of these to find their respective derivatives, but within the framework of a product rule. So now, putting all of that together, I'm going to be multiplying f prime times g. So that is 3 sine of x squared times cosine of x times g, which is the natural log of x squared minus x plus 1, plus f times g. So sine of x cubed times 2x minus 1 over x squared minus x plus 1. So my derivative looks like this big, huge, long function. So even though we know how to do the product rule, oftentimes we have to use other rules within the product rule to get our final answer. As long as we're careful and methodical about the way we do it, we should be able to find the solution. Let's try one more. Find the derivative of f of x equals e to the x over x to the fifth using the product rule. Now this is in a different shape or form than the other problems we've looked at. In order to be able to use the product rule, we need two functions that are multiplied together. This has a structure of one function over another one. So if we want to use the product rule, we have to figure out a way to rewrite this so that we have two things multiplied together. So one of the things we can do algebraically is we can bring up the term from the denominator if we make that 5 negative. So if we rewrite this as e to the x times x to the negative 5, it's now in a form where we can use the product rule. So here my f will be e to the x, and my g will be x to the negative 5. The derivative of e to the x is e to the x, and the derivative of x to the negative 5 is negative 5x to the negative 6. Remember, if you subtract 1 from a negative power, it becomes more negative. So now applying our product rule, we're going to do f prime times g. So we have e to the x times x to the negative 5 plus f times g prime. So e to the x times negative 5x to the negative 6. So if we want to simplify our derivative a little bit, we can make some of those powers positive again by putting them back down in the denominator. So the first term I would probably simplify into e to the x over x to the positive 5. So I'd bring that term down by changing the power back to positive. The second term here, notice that I have a negative 5. I'm going to pull that to a front. So that's going to be minus 5e to the x. So there's my 5, there's my e to the x. And now my x to the negative 6, I'm going to put that down in the denominator and make it x to the positive 6. So now my first derivative looks like two quotients here, but we were able to find these using the product rule because we were able to bring the denominator up.